Welcome to the Explainer. Today, we're diving into how AI learned to see. We'll trace the incredible journey from models that needed millions of human-labeled photos to ones that can now, pretty amazingly, teach themselves.
So, let's kick things off with the central puzzle researchers were banging their heads against for years. You know, the old way of teaching an AI what a cat is, you'd have to show it thousands, maybe millions of pictures, each one meticulously labeled cat by a person. But that's incredibly slow, it's expensive, and it just doesn't scale. So the big question became, there has to be a better way, right?
And the answer, it turns out, is this revolutionary idea called self-supervised learning. The best way to think about it is like this. Instead of a teacher telling the AI, hey, this is a cat, the AI gets a giant, messy pile of unlabeled photos and has to figure out the patterns all on its own. It's kind of like solving a massive visual jigsaw puzzle without ever seeing the picture on the box. The model literally learns by teaching itself. So, how did we get from that big aha moment to where we are today? Well, here's our roadmap. We're going to start with a clever technique called SimCLR. Then we'll see how researchers hit a major wall and had to get creative. After that, a whole new kind of AI brain called a vision transformer enters the scene. And finally, we'll put all the pieces together to understand the secret sauce behind DINOv2. All right, let's get into it. Our story really kicks off back in 2020 with a paper called SimCLR. Now, this was an absolute game changer because it introduced this really elegant, really simple way to teach a machine what similar means without using a single human label. So here's how SimCLR works, and it's pretty clever. You take one image, let's say it's a photo of a car. You then create two slightly different versions of it. Maybe you crop one and you change the colors on the other. You feed both of these into the AI, and the AI's entire job is to learn one simple rule. These two images, which both started as the same car, are a match. And every other image in the batch, they are not a match. It's learning by contrasting what's the same from what's different.
So this distinction is absolutely crucial. A positive pair is just those two different versions of the same image. The model's goal is to see these two as being as similar as possible. Everything else in the training batch, pictures of cats, dogs, trees, you name it, they all become negative pairs. The model's goal there is to push them as far away as possible. It's learning what a car is by learning what it isn't.
But, and this is a big but, there was a huge catch. For this whole contrastive thing to work, SimCLR needed to see a ton of not a match examples in every single training step. This meant using gigantic batch sizes. We're talking over 8,000 images at once. That requires an insane amount of computing power, which made it super expensive, and a major roadblock for, well, almost everyone.
This reliance on huge batches and all these negative pairs was a serious bottleneck. It really limited who could even attempt to train these models, and that frustration sparked the next big wave of innovation. It all centered on one critical question. Do we really need all those negative pairs?
And here's the intuition behind that question, right? The problem with negative pairs is they treat all different images the same. So to the model, an image of a truck and an image of a dog are both just not a car. That just feels wrong. I mean, a truck is visually a lot more similar to a car than a dog is. The model wasn't learning any of those important nuances. So researchers asked this brilliant and honestly kind of counterintuitive question. What if we could learn only from the positive pairs? What if a model could learn all the rich visual features it needs just by comparing two different views of the exact same image, without having to contrast them against a whole sea of negatives?
The breakthrough came from a paper called BYOL, which introduced this super clever student-teacher setup. Imagine you have a student network that's learning, and it's trying to learn from a very wise but slightly slower teacher network. The student looks at one version of an image and tries to predict what the teacher will say about another version of that same image. But here's the trick. The teacher is just a slightly older, more stable version of the student itself. This elegant little dance between the two was enough to learn powerful features, and this was a huge deal because it completely got rid of the need for negative pairs and those massive batch sizes. Suddenly, this research was way more accessible. Building on that momentum, a paper called Suave added two more powerful ideas to the mix. First, clustering. So instead of just saying, these two images are similar, the model had to start sorting images into different buckets or categories that it came up with on its own. Second, it used a multi-crop strategy.
This meant showing the model not just the whole picture of a car, but also little close-ups of a wheel or a headlight or a door handle, and teaching it that all these little pieces belong to the same big thing. This forced a much deeper, more robust understanding of objects. Okay, so the learning methods themselves were getting way more sophisticated, but they were all using the same underlying engine, a type of neural network called a CNN, which had been the gold standard for computer vision for years. But that was all about to change in a big way. The DINO paper took that awesome student-teacher framework we just talked about and paired it with a completely different kind of neural network architecture, the Vision Transformer, or VEET for short. Now, VITs were already taking the world of language processing by storm, and DINO was the first to show that they could be an absolute game changer for self-supervised vision too. And this is where something just amazing happened. When the researchers looked under the hood at the model's internal attention maps, they saw that the model was automatically learning to separate objects from their background. It was essentially drawing outlines around things in the image without ever being told what an object even was. It was learning the structure of the visual world completely on its own. The last major piece of the conceptual puzzle came from a model called iBot, and it borrowed another genius trick from the world of language models: masking. You know how a language model might have to guess a missing word in a sentence? Well, iBot would do the same for images. It would randomly hide little patches of an image from the student network, and the student's job was to predict what was in those missing patches. This forced it to develop a much deeper, more contextual understanding of the entire image. So we've seen all these incredible innovations, each one building on the last. So the question is, what happens when you combine all of these powerful ideas into one single supermodel? Well, that's exactly what the creators of DINOv2 did. And what's really interesting here is how you can just see the entire story playing out in just a couple of years. It's this direct lineage of ideas. BYOL solves the big problem created by SimCLR, Suave adds cool new abilities, DINO swaps out the engine for a more powerful one, and then iBot adds a new learning technique on top. Each paper stands directly on the shoulders of the ones that came before. And that brings us to the final recipe for DINOv2. The brilliant part is that it's not one single new invention, but a masterful combination of the best parts of everything we've talked about. It takes that student-teacher idea, it powers it with that new Vision Transformer engine, and then it uses a clever mix of learning goals. One goal forces it to understand the image as a whole, while another forces it to understand the fine-grained details by filling in those missing patches. It's truly the best of all worlds. But there was one final, crucial ingredient to its success. And that was massive, massive scale. The DINOv team took this perfected recipe of ideas and trained it on a huge, carefully curated dataset of 142 million unlabeled images. By combining all the best techniques and just applying them at a scale no one had seen before, the model achieved its groundbreaking, state-of-the-art performance. So think about it. We've gone from painstakingly labeling millions of images by hand to creating AI that can learn the visual world on its own just by looking. This journey from SimCLR to DINOv2 isn't just about better image recognition. It's a fundamental shift in how we build intelligent systems. It proves that with the right approach, machines can make sense of our world without us holding their hand every step of the way. And that leaves us with this huge, fascinating question. If AI can teach itself to see, what will it be able to learn next?